In this video, I'm going to show you how to find normal depth for a partially full circular pipe like this. So this is the cross-sectional area of the circular pipe, and this is the level of water. We're going to call it normal depth because our flow is steady and uniform. This is the center of the pipe, and we're going to add some variables to this figure to be able to calculate y sub n. All right, but first of all, why is it going to be important? Why do we need to find normal depth for a partially full circular pipe? This is going to be important when you are learning about culvert design and you want to design a culvert that is not full and the barrel of the culvert is circular. You're going to use this theory. All right, so with that, I'm going to define some variables over here. All right, the first thing that I'm going to define is this angle. This angle, I'm going to call it theta. And then there will be another angle over here. This I'm going to call alpha. So notice that alpha and theta are both in radian. All right. There are some depth that I want to, and length that I want to define. So this length, for example, from the bottom of your channel, your pipe, to the center of it, this is the radius of the circle, right? Or diameter divided by 2. The other thing that I want to define is this length. This length, so if this length is radius, or in other words, if this length is diameter divided by 2, or radius, then this length would be d divided by 2 times cosine of alpha. And also this length, the horizontal length over here, would be d divided by 2 sine of alpha. All right, now that we have all these lengths defined, if I ask you how do you find the value of yn based on all these lengths, you would tell me that it would be this length plus this length. So it's going to be d divided by 2 plus d divided by 2 cosine of alpha. All right, now I'm going to convert all the alphas in all the equations that I'm going to write over here to theta. That's going to make it easier for me. To do that, I know that 2 alphas plus theta is going to be equal to 2 pi. In other words, 2 alpha plus theta is equal to 2 pi. So from this, I can write that alpha is equal to pi minus theta divided by 2. All right, I can take this and put it over here. But before that, I'm going to show you that, okay, so I know that cosine of alpha is equal to cosine of this term, which is pi minus theta divided by 2. From trigonometry, you remember that cosine of pi minus whatever is negative cosine of that angle that you have. So this is going to be equal to negative cosine of theta divided by 2. All right, so instead of cosine of alpha in this equation, I'm going to put negative cosine of theta divided by 2 and write the yn equation over here. Yn would be 1 minus cosine of theta divided by 2. All right, so this is the equation for normal depth. As you can see, the equation for normal depth is a function of theta as well. We don't have the value of theta, so we need to find another relationship that gives us theta, so we can put it in this equation and find the value of yn, or normal depth. That auxiliary equation that we are going to use is Manning equation. If you don't know what Manning equation is, or if you don't remember it, or if you want to review it, I link a video below that you can see where Manning equation is coming from. N is Manning's roughness. A is the cross-sectional area of the flow. Notice that A is not the cross-sectional area of the pipe. It's cross-sectional area of the flow. and then r, or hydraulic radius, to the power 2 over 3, and then s sub 0, which is the slope of the channel, to the power 1 over 2. R, or hydraulic radius, is wetted perimeter, which is this length, that is wetted, divided by cross-sectional area of the flow. All right, so what I'm going to do is to calculate cross-sectional area of the flow, calculate wetted perimeter of the flow over here, put R and A in this equation. All of these are in terms of theta, and then I will find an equation in terms of Q and theta. Since the value of Q is normally given, you have your design flow, then you will find the value of theta from the equation that we are going to develop, put it over here, and you will be able to find normal depth. All right, let's do that. So the first thing that I want to do is to find the value of cross-sectional area of the flow. So cross-sectional area of the flow, let me actually change the marker to be able to show you. If I want to figure out the cross-sectional area of this flow, I'm going to divide it into some familiar geometric shapes. So I'm going to divide it into this area, which is the area of the major sector of the circle. So I can easily calculate this area. Also, I can easily calculate this area. This is a triangle, right? So I can calculate the area of this triangle too. So that's exactly what I'm going to do. The area of the major sector of the circle is going to be like this. So I know that area of the circle is pi divided by 4, diameter to the power 2. This is the area of the entire circle. But I'm looking for the major sector that has the angle of theta. So I'm looking for only theta out of 2 pi. Perfect. So this is the area of the major sector. Now the area of the triangle, half of its base. So this is half of its base. So I need to put 2 times d divided by 2 sine of alpha. So it would be 2 times d divided by 2 sine of alpha. This is base of the triangle, and the height of the triangle is equal to d divided by 2 cosine of alpha. All right. Let's organize this equation and write it over here. Pi and pi will cancel each other out, so you will have cosine of alpha. You probably remember from trigonometry that this should be familiar to you. So let me write this over here. From trigonometry, you remember that sine of any angle times cosine of that angle is equal to half of sine of 2 times that angle. Right? Okay. So we know this. Also, we know that 2 alpha is equal to 2 pi minus theta, right? So we know about this part of it. 2 alpha is equal to 2 pi minus theta, right? Okay. So I'm going to use this and write it and simplify this equation. This would be equal to and from trigonometry, this is going to be 1 over 2 times negative sine of theta. All right, I'm going to put this right over here and then simplify this equation. Eventually, area is going to be, all right, so this is going to be the area when you have normal flow. So when you have normal flow, this is going to be your area. That's why I added this n over here. So this was another equation that we are going to use. Now that I have the value of a sub n, or the area of flow for normal depth, I can put it over here. But before that, I need to calculate P, or wetted perimeter. Wetted perimeter is this length, the wetted length. To calculate that, first of all, if I ask you what would be the perimeter of this circle, you would tell me that it would be 2 pi r, and r is the radius. So it would be 2 pi r is the radius, so diameter divided by 2, right? This is the perimeter of the entire circle. But are we looking for the entire circle or just a portion of it, a chunk of it? We're looking at only this chunk, right? And that chunk is theta over 2 pi, right? Okay, so this would be the wetted perimeter that we are looking for. And this 2 pi will cancel out with this one, and it would be, all right, now that we have the value of wetted perimeter and area, we are ready to put these two values into the Manning equation and come up with an equation that has Q in it and theta in it. Let me write down the finalized equation for you. The finalized equation is in this term. Theta minus sine of theta to the power of 5 over 3 divided by theta to the power 2 over 3 is equal to 20.16 times Manning roughness, Q, diameter to the power 8 divided by 3, and slope to the power 1 over 2. All right, so this is the Manning's equation when you have a circular pipe that is partially full. Now, take a look at this equation. We have theta in one side and Q in another side. Normally, we do have the diameter, we do have the slope, we do have the Manning roughness, and also we have the Q. So the only value that we don't have in this equation is theta. Theta can be found numerically, and then once you have theta, you will put it in this equation to be able to find yn, which is your normal depth. This is the theory of finding normal depth, or yn, for a circular pipe that is partially full. Now, if you want to see this theory in an example, in next video, I'm going to show you how you can use Excel or how you can use other programming languages, write a couple of lines of codes to be able to solve these equations numerically.